Hello everyone, in this video we'll be solving problem 53, maximum subarray. The problem statement is, given an integer array nums, we need to find the subarray with the largest sum and return its sum. In example number 1, with this as our input, the largest sum of the subarray is 6, which starts from 4 and ends at 1. Similarly, in example number 2, we have only one element in the array, which is 1. So the largest sum is going to be 1, as all of the elements in the array can also be considered as part of a subarray. I hope you were able to understand the problem statement. It is very easy and straightforward. So let's switch to whiteboard and discuss how we can solve this problem. Let's take this as our example. The simplest way to solve any problem is to use a brute force approach, where we'll try to identify all possible combinations of subarray, record its sum, and then compare it with the max sum. This max sum will be updated only when the temporary sum that we calculated for any of the subarray is greater. After we have iterated through all of the possible combinations in the given array, we'll return the maximum sum as our output. Let's do a couple of simulations to understand this approach better. We'll begin with the starting pointer pointing at index 0, while the ending pointer will be pointing at index 1, that is start plus 1. With these two values, our subarray would have 5 and 4 in it. The total sum is going to be 9. We'll compare it with the max value, which will be 0 by default. So between the two, as 9 is greater, we'll save 9 into this max value variable. Moving on, the starting index will stay the same and we'll only be updating the ending index until it reaches the last element in the array. So the next element is 2. My subarray will have 5, 4 and minus 1. The total is 8. As 8 is smaller, I will not save it in the max variable. Moving on by incrementing the end pointer to 3. The values will be 5, 4, minus 1 and minus 7. The total is 1. Again, it is smaller, so I will not update the max variable. Once we go through the combination of the starting index as 0 and the last index as 4, we'll then increment our start pointer to 1 and the end pointer will always be greater than 1, so 2. And we'll try the same combination. So this time it's going to be 4 and minus 1. Take the sum, which is 3, compare it to the maximum, and then if it is greater, we'll save it. We'll continue to build all possible combinations of the subarray to calculate the maximum. With this solution, our time complexity is O of n square, where n is the number of elements in the input array. This is because we are running nested loops to identify all possible combinations of the subarray, calculate its corresponding sum, and compare it with the maximum sum to get the best results. While the space complexity is O of 1, as we are only using couple of variables to record the temporary sum of the subarray and then one variable to record the maximum sum that will be returned as the output. As the time complexity of this approach is very high, let's discuss if there is an optimized solution available. Before we directly jump into how to solve this problem, I would like to discuss a couple of concepts that will help us derive that solution. Let's say I have two numbers, 2 and 5. Let's assume 2 is the sum of few numbers in an existing subarray. We need to decide if we should include the next number, that is 5, to the existing subarray. If I include 5 into the subarray, the total will be 7. As 7 is greater than the original subarray total, which is 2, it makes sense to include 5 in the subarray. Now this is a positive case. Now let's discuss a different negative case. Let's assume the subarray total is 5 and the new number is minus 1. The sum of these two numbers is going to be 4, which is actually lower than the original subarray total. So it does not make sense to include minus 1 into the existing subarray and lower the total. So far the scenario that we looked at, the original subarray totals are positive. Now let's take a third scenario where these original numbers are negative. Now let's say my subarray total is minus 4 and the next number is 6. So if I add these two together, the sum will be 2. If I compare this with the original subarray, the value is greater. So it makes sense to include 6 into the existing subarray. But if we compare 6 with the new total, 6 is greater. So instead of adding 6 to the existing subarray and getting a lower result, we should start a new subarray with 6 in it. As the intention is to get a subarray with the maximum total, this is one condition that we should take into account when building the subarray. As we don't need to record the elements that are included in the subarray, we can compare the total with the new number that we are trying to add and accordingly update the sum. So this is the premise behind Kadane's algorithm. We will keep a running score of the total of the subarray and compare it with the next number that we are trying to add. If the sum is greater than the new number that we are trying to add, we will include the new number into the existing subarray, or else start a new subarray with the new number as the first element. Let's run a short simulation of Kadane's algorithm on the input and verify the results. So in Kadane's algorithm, we'll use two variables. Temp sum will hold the value of the subarray that we are trying to build, while the maximum sum will hold the sum of the maximum subarray that we encounter during the iteration. We'll set the temporary sum and the max sum to the first element in the array, assuming that we have a subarray with the first element in it. Incrementing our pointer to the next element, that is 4. We'll use the formula that we discussed earlier, where we'll compare 4 with the sum of 4 and the existing subarray total, that is temp sum. As temporary subarray sum value is 5, the sum will be 9. After comparing 4 and 9, as 9 is greater, it makes sense to include 4 in the existing subarray. So we will update the temporary sum and the max sum to the new values, which is 9. Moving on to the next element, minus 1. We'll repeat the same cycle of comparing minus 1 with the sum of minus 1 with temp sum. RHS value will be 8 as temp sum is 9. Between the two, as 8 is greater, 8 will be our new temporary sum, but because it is smaller than the maximum sum, we will not update it. Moving on to the next element, that is minus 1. On the left hand side I'll have minus 1, and on the right hand side it will be minus 1 plus 9, which is the temporary sum. Between 8 and minus 1, as 8 is greater, this should be saved in the temporary sum. The new value will be 8, and between 8 and 9, as 9 is greater, we will not update maximum sum. Next value is minus 6. Minus 6 on the left hand side and minus 6 for temporary sum. Minus 6 plus 8, the result is 2. And between minus 6 and 2, 2 is greater, so we'll save 2 in the temporary sum variable. And between 2 and 9, 9 is greater, so we'll not update the maximum sum variable. Moving on to the next element, which is 8. So in the table, we'll have 8 on the left hand side, 8 plus temporary sum, so 8 plus 2, total is 10. Between 8 and 10, as 10 is greater, this will be our new temporary sum. And between 10 and 9, 10 is greater, so we'll replace maximum sum with 10. As we are done with the iteration, at the end we can return maximum sum as our output. With this solution, our time complexity is O of n, where n is the number of elements in the input array. As we are running the iteration only once, the time complexity is O of n, while the space complexity is O of 1, that is constant space, because we are using these two variables to record the temporary sum of the subarray and the maximum sum. I hope you are able to understand how Kadane's algorithm worked and how it was helpful in solving the problem. Let me show you how we can implement the very same solution using Java. In this Java implementation, I've created two variables, best sum and the current sum, setting the default values to the first element in the array. After that, I'm starting a for loop to iterate through all of the elements starting with I is equal to 1. Inside the loop, I'm using the math.max operation to compare the current value that I is pointing with the combination of the current sum and the current number that I is pointing at. Whichever is higher is going to be saved back into this current sum variable. On the next line, I'm comparing the best sum with the current sum, and whichever is higher is saved back into this best sum variable. After the for loop is complete, I am returning best sum as the output. This code, when submitted on LeetCode, beats nearly 100% of the submissions in terms of runtime and nearly 57% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.